Logical connectives. Recall the following logical connectives: and, or, if then, if and only if, not. We use a wedge symbol for and, a V symbol for or, a right arrow for if then, a double arrow for if and only if, and a tail dash symbol for not. When we combine two statements using the word and, the resulting statement is called a conjunction. Similarly, for or, we get a disjunction. For if then, we get a conditional or implication. For if and only if, we get a biconditional. And for not, we get a negation. We will use the wedge symbol to represent the logical connective and. The compound statement P wedge Q is called the conjunction of P and Q. It is pronounced P and Q. P and Q is true when both P and Q are true, and it is false otherwise. We can use a truth table to display the possible truth values of P and Q. We start by labeling the columns of the table with the propositional variables that appear in the statement, followed by the statement itself. So we have P, Q, and P and Q. We then use the rows to run through every possible combination of truth values for the propositional variables, followed by the resulting truth values for the compound statement. True, true gives true. True and false gives us false. False and true gives us false. False and false gives us false. The truth table for the conjunction is based upon the way we use the word and in everyday English. For example, suppose that Jamie is a girl with black hair. Then the statement Jamie is a girl and Jamie has black hair is true because each of the statements Jamie is a girl and Jamie has black hair are true. Similarly, the statement Jamie is a girl and Jamie has red hair is false because the statement Jamie has red hair is false. Based upon your own experience of the English language, you may be able to compute the truth value of a conjunction of two statements without needing to look back at the truth table. Let's look at an example. If P is true and Q is false, then we can compute the truth value of P and Q by looking at the second row of the truth table for the conjunction. We see from the highlighted row in the truth table that if P is true and Q is false, then P and Q is false. Using the three-line symbol for is logically equivalent to, we can write P and Q, three-line, true and false, three-line, false. This can be read, P and Q is logically equivalent to true and false, which is logically equivalent to false. Or more simply, P and Q is false. Let's try an exercise. Determine the truth value of P and Q given that P and Q are both true, P and Q are both false, and P is false and Q is true. Now's a good time to pause the video, try this exercise, and then resume it to check your answers against mine. Let's look at the truth table for P and Q. If P and Q are both true, then we have true and true is true. If P and Q are both false, we have false and false is false. And if P is false and Q is true, we have false and true is false. We will use the V symbol to represent the logical connective or. The compound statement PVQ is called the disjunction of P and Q. It is pronounced P or Q. P or Q is true when P or Q or both are true, and it is false when P and Q are both false. Let's look at the truth table for P or Q. We have true or true is true, true or false is true, false or true is true, and false or false is false. The truth table for the disjunction is based upon the way we use the inclusive or in everyday English. For example, suppose that in order to be able to watch television, Kelly's parents tell her that she must first either do the dishes or clean her room. In this context, the statement, Kelly does the dishes or Kelly cleans her room, is understood to be true if Kelly does the dishes or Kelly cleans her room or both. Certainly, if she completes both of these tasks, it would be unnatural to penalize her. In mathematics, when we use the word or, we always assume that we mean the inclusive or unless we are told otherwise. In English, when we use the word or, we are more likely to be using the exclusive or. For example, if a waiter says you can have fries or a salad with your order, it is unlikely that he means you can have both. This is an example of the exclusive or. Let's try another exercise. Determine the truth value of P or Q, given that P and Q are both true, P and Q are both false, P is true and Q is false, P is false and Q is true. Again, you should pause the video and try this exercise yourself first, then resume the video to check your answers. Looking at the truth table for P or Q, let's see. If P or Q are both true, then we have true or true is true. We have false or false is false. We have true or false is true. And we have false or true is true. We will use the right arrow symbol to represent the logical connective if then. The compound statement P implies Q is called a conditional or implication. It is pronounced if P then Q or P implies Q. P implies Q is true when P is false or Q is true or both, and it is false when P is true and Q is false. Let's look at the truth table for P implies Q. We have true implies true is true, true implies false is false, false implies true is true, false implies false is true. In the conditional P implies Q, P is called the hypothesis or assumption or premise, and Q is called the conclusion. The truth table for the conditional is loosely based upon the English meaning of if then or implies. However, trying to understand this truth table by analyzing English sentences often leads to confusion. So in this case, it may be more instructive to understand what we wish to accomplish with this connective mathematically. When should P implies Q be true? Well, we would like P implies Q to be true if the assumption that P is true forces Q to be true as well. Equivalently, if the hypothesis is true, then the conclusion must be true. For example, let's take the statement, if Odin is a cat, then Odin can bark. Now, if Odin happens to be a cat, then the statement just given in quotes is false. Do you see why? The hypothesis Odin is a cat is true. If the conditional were true, then the conclusion Odin can bark would be forced to be true. However, cats can't bark. So the conditional is false. This situation corresponds to the second row in the truth table for the conditional. On the other hand, the statement, if Odin is a cat, then Odin can meow, is most likely true. This time, the hypothesis and conclusion are both true. This situation corresponds to the first row in the truth table for the conditional. What about the situation in which the hypothesis is false? In this case, we don't really care what the conclusion is. The conditional is true either way. When the hypothesis is false, we will say that the conditional statement is vacuously true. The word vacuous means empty. The idea is that something that is vacuously true is true for a very silly reason. For example, suppose that we are looking at an empty room and someone says, if there is a pig in that room, then it can fly. This is equivalent to saying every pig in that room can fly. This statement is true, but for a very dumb reason. Yes, every pig in that room can fly, simply because there are no pigs in the room. If there were even a single pig in the room, then the statement would be false. In order for someone to dispute our claim that every pig in the room can fly, they would need to show us a pig in the room that cannot fly. Of course, they cannot do this. After all, there are no pigs in the room. This notion of vacuous truth corresponds to the third and fourth rows in the truth table for the conditional. Let's try another exercise. Determine the truth value of P implies Q, given that P and Q are both true, P and Q are both false, P is true and Q is false, P is false and Q is true. Again, you should pause the video now, try this exercise on your own, then resume the video to check your answers. Let's look at the truth table for P implies Q. And starting with the first one, true implies true is true. False implies false is true. True implies false is false. And false implies true is true. We will use the double arrow symbol to represent the logical connective if and only if. The compound statement P double arrow Q is called a biconditional. It is pronounced P if and only if Q. P if and only if Q is true when P and Q have the same truth value, both true or both false. And it is false when P and Q have opposite truth values, one true and the other false. Let's look at the truth table for P if and only if Q. We have true if and only if true is true, true if and only if false is false, false if and only if true is false, and false if and only if false is true. Let's try another exercise. Determine the truth value of P if and only if Q, given that P and Q are both true, P and Q are both false, P is true and Q is false, P is false and Q is true. Again, pause the video now, try the exercise yourself, and then resume the video. Looking at the truth table for P if and only if Q, we have true if and only if true is true, false if and only if false is true, true if and only if false is false, and false if and only if true is false. We will use the tail dash symbol to represent the logical connective not. The compound statement tail dash P is called the negation of P, and it is pronounced not P. Not P is true when P is false, and it is false when P is true. In other words, P and not P have opposite truth values. Let's look at the truth table for not P. We see that not true is false, and not false is true. Since negation requires only a single propositional variable, there are just two possible truth assignments to worry about. The first column of the truth table, labeled P, gives the two possible truth assignments, true and false. The truth table for the negation is based upon the way we use the word not in everyday English. For example, since the statement fish swim is true, it follows that the statement fish do not swim is false. Similarly, Since the statement elephants fly is false, it follows that the statement elephants do not fly is true. Let's look at an example. If p is true, then we can compute the truth value of not p by looking at the first row of the truth table for the negation. We see from the highlighted row in the truth table that not true is false. Let's try another exercise. Determine the truth value of not p given that p is false. Again, pause the video, try the exercise, and then resume the video. Looking at the truth table for the negation, we see that not false is true. Now's a good time to just look at all the truth tables that we covered together. Here we see the truth tables for conjunction, disjunction, implication, if and only if, and the negation. Let's look at an example. Let P represent the statement ducks quack. Let Q represent the statement 0 equals 1. Rewrite each of the following statements in words and state the truth value of each statement. P and Q, P or Q, P implies Q, P if and only if Q, not Q, not P or Q, the negation of P or Q, not P and not Q. First, it's worth noting that P has truth value T, ducks do quack, whereas Q has truth value F. 0 is not actually equal to 1. P and Q can be written ducks quack and 0 equals 1. We have true and false is false. P or Q can be written ducks quack or 0 equals 1. True or false is true. P implies Q can be written if ducks quack, then 0 equals 1. True implies false is false. P if and only if Q can be written ducks quack if and only if 0 equals 1. True if and only if false is false. Not Q can be written 0 is not equal to 1. Not false is true. Not P or Q can be written ducks do not quack or 0 equals 1. Not true or false. Now, we should just point out here real quick before we do this that when a negation and another logical connective appear together without parentheses, we always assume that the negation is going to be done first. This is just a man-made order of operations that allows us to write statements that are more readable without having to have lots of parentheses. So we're going to do not true first, which is false, and we get false or false, which is false. The negation of P or Q can be written, it is not the case that either ducks quack or 0 equals 1. This can be written a little more nicely in English as neither can ducks quack nor is 0 equal to 1. We have the negation of true or false is the negation of true, which is false. Not P and not Q can be written as ducks cannot quack and 0 is not equal to 1. This statement can also be written in English as neither can ducks quack nor is 0 equal to 1, just like in number 7. We have not true and not false. Again, we give priority to the negation to get false and true, which is false. Let's look at numbers 7 and 8 once again very quickly. Notice that they both have the same English equivalent, and therefore it should seem that they would be logically equivalent, which they are. The negation of P or Q is logically equivalent to not P and not Q. This is known as one of De Morgan's laws. You get another of the De Morgan's laws by interchanging the roles of the disjunction and the conjunction. And we'll talk more about De Morgan's laws a little bit later. Let's do one more exercise. Let P represent the statement, frogs are birds, and let Q represent the statement, 2 is less than 1. Translate each of the following compound statements into English and compute the truth value of each statement. Once again, pause the video now, try this exercise yourself, and then resume the video to check your answers against mine. Let's first translate the compound statements into English. So P implies Q can be written if frogs are birds, then 2 is less than 1. Not P or Q could be written frogs are not birds, or 2 is less than 1. P if and only if Q can be written frogs are birds if and only if 2 is less than 1. P implies Q and Q implies P can be written if frogs are birds, then 2 is less than 1, and if 2 is less than 1, then frogs are birds. The negation of P and Q can be written, it is not the case that both frogs are birds and 2 is less than 1. And not P or not Q can be written, frogs are not birds, or 2 is not less than 1. Okay, now to compute the truth values of these statements, first observe that P and Q are both false. So we have false implies false is true, not false or false is true or false, which is true. False if and only if false is true. False implies false and false implies false is true and true, which is true. Not false and false is not false, which is true. And not false or not false is true or true, which is true.